The ideal gas equation is not applicable to real gases, and it's only at certain conditions of temperatures and pressures that the ideal gas equation is actually applicable to real gases. So it was modified by van der Waals, and he gave us the equation, van der Waals equation for real gases, or it's also referred to as van der Waals equation of state. Now, in the end of the previous video, there were two things that we discussed regarding the kinetic molecular theory of gases. So one of them was the fact that the volume of the gas itself was considered negligible in compared to the empty space. The other one was about how the intermolecular forces of attraction between the gas molecules are actually basically considered as they don't exist. Okay, so first of all, let's just go over that postulate. So here we have the condition of the gas, and we basically put that all over here, and it's clear that the volume of the gas is negligible compared to that of the empty space in between them. But that was an issue. So based on so this meant that the molecules are not able to move freely, but the free volume is less than the observed volume. So it was noticed that the observed volume and the free volume, there were different in terms of their values, and the free volume is actually less than the observed volume of the gas. And so Van der Waals suggested a term B. Now, V is considered to be the volume occupied by 1 mole of the gas. And so the volume that is available for the molecules for the movement is the corrected volume. So V corrected is V minus B for 1 mole. So basically, we're assuming that by 1 mole of a gas, certain amount of space is available, and that's the volume of the gas. So the volume which is corrected is going to be less than that of the expect the volume which is expected. So V corrected is going to be V minus B for 1 mole. For n moles, it's going to be V minus NB. And B is not equal to the actual volume. It's actually calculated that it was 4 times the actual volume of the gas. Okay, so that's correction due to volume. First of all, we assume that the empty spaces over here was way more than the volume occupied by these gas. But in reality, it was, it was not negligible. So there was a difference in terms of the volume that was observed. And when V is considered to be the volume occupied by 1 mole of the gas, we add something called a suitable correction term called B, and V corrected the corrected volume equals to V minus B for just 1 mole. For n moles, it's going to be V minus NB. And B is not equal to the actual volume of the molecules. And it was actually found to be 4 times the actual volume of the molecules. Now, the next one is correction due to intermolecular forces. Now, as I told you, the intermolecular forces of the gases, if it did not exist, then what would have happened is when we liquefied or we tried to liquefy the gas, no matter how much pressure you applied, gas wouldn't get converted from gaseous state to a liquid state. So it wouldn't get converted to a liquid state at all. But that's not the case. We know condensation as a process that takes place where a gas gets converted to a liquid. So there are attractive forces between the molecules that are present in the real gases. Now here you have two conditions. First of all, over here where the gas is against the molecule is near the wall, and so it is pulled in by these various molecules which are present. Whereas so it has a net inward force over here. So you have a force that is pulling it inside. On the other hand, when it's in the bulk of the particular, vessel, then this molecule is getting pulled by several molecules in all directions. So there is not going to be a net force which is present. So in the middle of the container, the molecule is actually attracted uniformly. On the other hand, the one which is in the closer to the wall of the container, it is not attracted uniformly. And when a molecule, so when it tries and approaches the wall of the containers, it gets pulled in by the other molecules which are present. So there are obviously certain intermolecular forces that make sure that this is taking place. If there were no intermolecular forces of attraction, this particular molecule wouldn't have been pulled inside by the molecules in the bulk of the vessel. So because there is a pull, right? This molecule will hit the wall slower than it should. Let me tell you again. So if this, let's assume this molecule was freely moving, okay, then if did not have any attractive force by these molecules, it would hit much faster. But that's not the case that was observed. It was observed that it is hitting the wall much slower. So then there has to be something that's happening, right? So it was noticed that these molecules are actually trying to pull this molecule inside, and so it's slowing this molecule down. So there is a difference in terms of the pressure, the observed pressure, which is lesser than the ideal pressure. So we will be correcting the pressure as well. So P corrected is equal to P plus P dash, where observed pressure is P and the correction term is P dash. And P dash equals to A by V square for 1 mole, and for n moles it's A by NV square. And A is considered as a constant, and it is the value of A depends upon the nature of the gas. So the P ideal value is going to be the P real value plus the correction term A n square by V square. I am sorry, this had to be for n moles. This is not over here, but it's over here. N square. Okay, so n square by V square for n moles. So corrected pressure over here, corrected pressure is P corrected. So P corrected is a total of P plus P dash, where P is the observed pressure and P dash is the correction term. Now here we notice that the observed pressure is less than the ideal pressure, right? So because of that, we are adding it. And the correction term is A by V square for 1 mole and AN square by V square for n moles. So the value of P ideal is going to be P real plus AN square by V square. Now, we will be substituting the corrected values. Okay, so we are assuming the P ideal is P real plus AN square by V square, where this is a correction term. And for volume, which is the corrected value of volume, V corrected equals to V minus NB for n moles. So we are basically substituting these two, I'm sorry, and when you see PV equals to nRT, so this P plus AN square by V square, that is the correction term for pressure, for the intermolecular force and force of attraction, and V minus NB is the correction term for the volume, which we did in the beginning of this video. We're just multiplying, and this equals to nRT, and this particular equation is for n moles of that particular gas. So and this equation is called as the van der Waals equation of state. So just to recap, there are two things. First of all, we assume that the volume of the gas itself was negligible in comparison to the volume of the free space between these gas molecules. On the other hand, that was not the case. So van der Waals suggested correction term B. So when we assume that the B is the volume occupied by 1 mole of the gas, the corrected volume is going to be V minus B. And B, the value of B depends upon the nature of the gas. And B is not equal to the volume of the molecule, but it was actually found to be 4 times the volume of the molecule. So this V corrected term is V equals to V corrected equal to V minus NB for n moles. On the other hand, the reason you have correction of intermolecular forces is that when you have a gas in molecule in the bulk of that particular vessel, it does not have any net force acting on it. So all the gases are going to pull it at all directions. On the other hand, the one which is closer to the wall of the container, what was noticed was that it did not hit the walls of a container as as fast as it should have in the absence of the intermolecular force. So this meant that there is some amount of intermolecular forces between these gas molecules, which is leading to the fact that this molecule is not hitting the walls of a container as fast as it would. So this in turn led to a decrease in the pressure the observed pressure was less than the ideal pressure. So P corrected is going to be P plus P dash. So the observed pressure P and the P dash is the correction term. And the correction term for P dash is A by V square for 1 mole and A n square by V square. This equation is wrong. A n square by V square for n moles. So P ideal is going to be P real, that is the observed pressure, plus A n square by V square, which is the correction term. And the value of A is also going to be dependent on the nature of the gas. Basically, A and B, both of them are going to be dependent on the nature of the gas. Now we're substituting the values of P and V in the ideal gas equation to get P plus A n square by V square whole into V minus NB equals to nRT for n moles of the gas. And this is called as the van der Waals equation of state. I hope you understood all of this. With that, we're done with the deviation of a real gas from an ideal gas behavior. In the next video, we'll be talking about liquefaction of gases.